Hey, thanks, Saket, for the introduction. So, in this talk, I will try to tell you about a few theoretical and algorithmic questions that come up in the context of responsible AI. My background is mostly theoretical computer science and mathematics, but over the years, I have ventured into these questions related to responsible AI. And there are some nice theoretical and algorithmic questions there. I will not touch upon all aspects of responsible AI. And I think in the workshop that follows, you will be exposed to a lot of practical questions related to real world applications. But here the focus will be just to give you some snippets of how good theoretical and algorithmic questions come up when you think of responsible or trustworthy AI. So, this responsible or trustworthy AI or machine learning is a buzzword these days. It kind of encompasses a bunch of properties. Uh, for example, privacy, fairness, robustness, transparency, interpretability. And the kind of theoretical questions that mostly come up are related to, can we capture these properties in the form of metrics? Are there any trade offs between these different kinds of metrics? Can we optimize for any of these metrics? And the algorithmic questions are naturally of the kind that can we get efficient algorithms for most of these theoretical questions that come up? So I will give you some glimpses of questions related to fairness and robustness mostly. And because I have worked mostly on fairness, robustness, and of late a little bit of interpretability aspects. So to give you some background, responsible AI has been a buzzword because worldwide there are AI regulations that are coming up. So the AI regulations are at our doorstep, basically. The European Union has its proposed AI Act, uh, and you can look at the document online, which is from 2021. So it's quite recent, where they are trying to bring in regulations for a lot of AI applications in, be it healthcare, be it any kind of technology. Like you can even imagine AI for, say, facial recognition and conversational AI. Uh, all other kinds of aspects of AI has been applied in, say, fintech. Like all loans are processed using AI, whether to give a loan to a person or not. That is handled by, in a way, machine learning algorithms. So when AI affects, say, resources that are available to individuals, or if AI affects, say, outcomes in terms of education or financial resources available to a person, even, say, the credit card transactions, whether they go through or not, they are handled by AI. So when it comes to all of these aspects, it's important to regulate AI, and people look at different aspects of regulation, where you want, if you want an AI model to be responsible, you would want it to satisfy a bunch of properties. And some of these properties that people have been studying are privacy, fairness, robustness, transparency, interpretability, etc. Uh, so the main reason why people want to regulate AI, or these decisions taken by algorithms that underlie these models, is because algorithmic decisions can amplify harms. It's not just that we are comparing human versus machine. The thing is, when we have algorithmic decisions, they can help you on one side to make something very large scale, uh, but with that scaling up, it can also amplify harms, sometimes even if the harms are unintended. Like it may not be intentional, but the outcomes may be biased, which is a problem with fairness. The other thing is, algorithmic decisions can be very efficient, but they may not be transparent. It might just be like a black box to you, and you don't know. Say, for example, a person gets uh, his or her loan application denied. The algorithmic decision might just give the decision and may not be able to give uh, an explanation for why you were at the receiving end of that decision. So these are sometimes complex black box systems. What happens is they are also interacting with humans, in the sense that the training data that is used for many of these machine learning models, it is labeled by humans, so it carries the human biases. Secondly, many times the decisions are not completely taken by the systems. The system just gives like an indicator, and the final decision is still taken by a human. So in that case, when they get applied in, say, policing or judicial systems, there these models, they are like complex black box systems interacting with humans, and eventually there is some output that affects individuals or groups of individuals, like, say, people of a certain race or a gender. So the other thing that happens with these AI models is that, or algorithmic decisions, is that they have unknown failure modes post deployment. Like, you might see a behavior on training data, but then when you deploy them on test data, you might get some kind of failure modes which are not easy to explain. And the practical reason for studying all of these aspects is that violations of responsible AI standards or responsible AI regulations, they can carry financial penalties for companies. So, which is why they have sort of an incentive to go after these problems. It can also cause bad PR for a company. It can also lead to losing customers. There have been multiple incidents of all of these kinds, and that's why these all of many of these questions, they have a very practical motivation. But in this talk, we will just try to look at some of them, where we'll try to see how people have formulated them and what kind of nice questions that come up. Now, if you want to take this entire landscape of responsible AI, the thing, as I said, there are these multiple aspects like privacy, fairness, robustness, transparency, interpretability. And in fact, they interact with each other, in the sense that you want a system that satisfies all of these properties. Like, you don't want them to satisfy only one of these properties exclusively and without worrying about the others. But when we want to study them theoretically, first, it's sort of like studying them separately is not the best, but we must start somewhere. So, which is why we would sort of pick one of these properties and see what kind of theoretical questions come up. The other thing is, although after studying each of these separately, we must try to look at them, at least pairs of them, or see how they interact with each other, whether the solution for one of them, does it create any problems for some other property, etc. There has been recent work also that tries to look at multiple properties jointly, or at least two properties jointly. Secondly, each aspect, like, say, if you take fairness, it has multiple different subtopics. Like, you could think of fairness in classification, fairness in regression, fairness in ranking, clustering, and so on. So, even each of these properties, if you want to study, there are multiple different subtopics. Like, say, in case of privacy, you may want to study, say, differential privacy, but in the context of a particular application. So, depending on where these algorithms or these AI ML models are applied, based on that, there might be one particular application. And by that, don't mean like application in the sense of, say, loan adjudication. I mean only in the theoretical sense, that whether it is for classification, or for ranking, or for clustering, and so on. So we may have to pick one of these. And now, what can theory do? So, the theory cannot really capture all violations of responsible AI regulation, because that basically amounts to quantifying laws, regulations, or ethics. Like, some of these questions related to fairness are questions in like questions about ethics, and we cannot really capture them with tangible or quantifiable metrics. So it may not always be possible, but that doesn't stop us from thinking of at least good theoretical metrics that can be efficiently handled, because at the end of the day we have to build these systems, we have to deploy these systems, we have to see what problems occur, we have to fix those problems. The other criticism that often comes up is that if we try to fix these problems using by again proposing the ideas that we know, there has been like criticism that, oh, can algorithms fix algorithmic bias? So that has been a common criticism. Yes. So typically people build processes, or there is also a non-theoretical aspect of solving these problems to get the right processes in place and to get the right auditing mechanisms in place. But we should also look at theoretical auditing strategies or mitigation strategies for each of these problems. Like, can we efficiently check whether a given system is fair, or is, say, sufficiently transparent, or is sufficiently robust to certain changes in the data. So the other thing that comes up is what kind of models to study. So, as I said, first of all, we have to look at whether it is classification, clustering, ranking, etc. And again, people may want to sort of say that we want to study deep neural networks or these large language models. And studying maybe simple linear models in this context may give something theoretically interesting, but may not be useful. But that's not the case. In fact, actually, good theoretical and algorithmic questions exist at both ends of the spectrum. You might think of very simple questions like, say, fairness in linear regression or robustness in linear regression. And there are useful takeaways that one can apply even to deep neural networks or very large models or complex models, which where the takeaways are from understanding simple models. And also there are other at the other end of the spectrum also, one can define good theoretical and algorithmic questions. It's not the case that these models are completely opaque and we cannot do much about them. Now, one of the things that comes up when studying these properties in the context of responsible AI is that we want to have definitions of these harms, that because we said that the algorithms can or algorithmic decisions can amplify harms, we need some sort of definitions of these intended or unintended harms. For example, like the simplest kind of harm would be representation harm, in the sense that there are two groups, like, say, two races or two genders, and the decisions taken by these algorithms or models, they have representation harms in the sense that they overly represent one of the groups and underrepresent the other group. Sometimes these could be allocation harms, where the algorithm or the model, it does resource allocation. Like, for example, when a bank gives out loan, it's actually giving economic resources, it's providing economic resources. Or when, say, such systems are applied in college admissions, they are allocating educational opportunities to people, and there could be allocation harms. uh, there could be also the third kind of harms, which are like quality of service harms, where there is a model that behaves poorly for one language compared to some other language, like a, say, text completion model that behaves poorly for Spanish versus English, or, say, in a country like India, there are many languages, so we could think of these kinds of quality of service harms based on a lot of diversity that we have. That a model that only works for majority may not do well for minority. And this also has other implication in terms of losing, say, customers or users of a particular group, because if the model does not behave uh, well for a certain group, they have a tendency not to use the model. So in that sense, one can also link it to some tangible changes that happen to the model or its future long-term outcomes. Uh, Then there is also like lack of predictability or transparency related harms, where the model may not behave in a predictable way, which is what comes up typically in robustness, that you would have two individuals for whom the model should behave or the decision should be similar, but it is not similar. This happened in the context of, say, Apple had this card. So Apple card, there were complaints about gender bias where people said that they were husband wife, they were filing joint tax returns. So basically, their credit worthiness should be similar. They also jointly held all the assets. Their credit scores or their credit worthiness, as assessed by any model, should be similar, but the model was treating them differently. It was giving more credit to one person than the other. So there it was. It is a issue of group fairness because these two individuals are of different gender, but it was also an issue of predictability or robustness, where these two individuals have similar features. The model should treat them similarly. The predictions or the decision should be similar for them, but they were not similar. Okay, so with that as like a background, let me just tell you a little bit about fair classification. And let's think of what kind of notions people study when it comes to fair classification. I will also tell you a little bit about, because I mentioned theoretical questions, how they solve these problems and certain things that we care about, like for example, randomness, how randomness plays a role uh, in this, how randomness plays a role in fair classification. So in binary classification, we are given a joint distribution on features and class labels. So here X denotes the features and Y denotes the class label. And this capital X comma capital Y, that's a random point from this distribution. And the goal is to find a classifier that maximizes the accuracy, let's say, which is the probability that f of x equals y. F is that classifier. It is also, in for simplicity, let's say the class labels are binary, positive or negative or 0 1, and the classifier is also binary in the sense that it's a 0 1 deterministic 0 1 function. Okay. And in fair binary classification, what we want is, along with these features, every input also has a group membership. That is, now the joint distribution is on features, binary class labels, and the group membership, which could be like race or gender. And the goal is to find a classifier F that maximizes the accuracy, that is probability of getting the class label right, subject to some fairness constraints. Now, what kind of fairness constraints these could be? So the easiest thing to think of are these, or the natural thing to think of are group fairness. And in many cases, they also encode what are the corresponding laws about. So there are many laws, especially like in the US, there are these laws related to employment and housing, which gave rise to many of these definitions. That even in like, so F, the classifier, may not be intentionally doing any discrimination, but its outcome should not be discriminatory in a, when measured using a particular metric. So, for example, demographic parity says that it should have equal acceptance rate. That the probability that f of x equals 1, conditioned on the group being 0, should be equal to the probability that f of x equals 1, conditioned on the group being 1. And equal opportunity is another group fairness notion, which says that we want equal false negative rates. That is the probability that f of x is 0, that is the prediction is 0 when the true class label is 1. This happening on group 0 should be similar to the probability that f of x is 0 conditioned on the class label being 1 and the group being 1. So across these groups, z equals 0 and z equals 1, we should have equal false negative rates. That's what equal opportunity constraint means. So fair binary classification is basically maximizing accuracy subject to a constraint of this type, where it could be equal acceptance rate, equal false negative rates, equal accuracy across two groups, and so on. So many such definitions are available. One has to pick the group fairness constraint carefully in a way that closely captures the harm in the particular application that one is studying. So, for example, in case of loan adjudication, it could be like you don't want to deny loans to people who are credit worthy. So, depending on the application, the correct notion of uh, group fairness may vary, but the problem roughly remains the same. And for simplicity, let's think of the problem as maximizing accuracy subject to a group fairness constraint, which is either demographic parity constraint or equal opportunity constraint. One could also relax these constraints further to say that, okay, we don't want exactly equal uh, acceptance rates, but the acceptance rates, their difference across two groups should be at most epsilon. So one could also think of maximizing accuracy subject to the DP difference being at most epsilon. Or one could say that, oh, I want at least some accuracy, and subject to that, I want to minimize the DP difference. Like these, like equivalently, one could think of these problems. Now, if you look at just binary classification with two groups, if you don't think of fairness, if you only want to maximize accuracy, then the classifier of maximum accuracy is the Bayes optimal classifier, and it has been characterized as follows: that the maximum accuracy classifier f star of x is an indicator of eta x, whether that is greater than or equal to half or not, where where this eta of x is probability that y equals 1 conditioned on the features. So conditioned on the features, the probability of label being 1, if that is more than half, your classifier should classify that point as 1. Otherwise, it should classify that point as 0. And one can show easily, or we will also come to a short proof of this later in a couple of slides, that this is the classifier of maximum accuracy on that given distribution. Now it need not be DP fair or EO fair. So for example, if you look at this figure, it shows two populations, two demographic groups, let's say a red group and a blue group. And on the x-axis is their probability of this was in the context of recidivism, in the sense that the probability that a person would commit a crime again. And this is from Compass data, where which is a famous data set, which is it tells you it was used, a model was used in the US judicial system, where it sort of told the judge whether to give parole to a person or not. And basically, it was trying to predict the probability that a person committing a crime again after being on parole. So, but ignore that for a moment. Just think of the x-axis as probability that y equals 1. So, and the x-axis is density, or in a way proportion of the population that has probability of y equals. So if you have on x-axis a probability p, the y-axis tells you what fraction of the population has probability that y equals 1 conditioned on x equals little x equal to p. So the rightmost end of x-axis tell you the most risky individuals, and the left end of the or the individuals whose label is more likely to be 1, that is at the right end, and the individuals whose label is more likely to be 0, that comes at the left end. Now this maximum accuracy classifier would just put a uniform threshold at half, and it would give its prediction based on that, which means that population that you see, the shaded red region, that will get classified as 1, and the shaded blue region, that will get classified as 1 for from both these demographic groups. Now, that underlying population, there the number of people or this acceptance rates may be different for the red and the blue population. So the max accuracy classifier need not be DP fair or EO fair. Uh, Whereas if you look at a random classifier that just classifies every individual, with for every individual it just tosses a coin. It doesn't care about what eta x each. So think of eta x as the true risk. That is the probability. So for that individual whose features, so individual is encoded just by his or her features, which are given to us as x. And for that individual, we know what is the given the features, we know what is the probability of the label class label being 1. Now, for each individual, if you just toss a coin, which is half, which is basically a uniform random coin that gives you 1 or 0 with probability half half, and you just use that as the outcome, that random classifier will be DP fair, because it will have the same acceptance rate for every individual and therefore for every group. Also, it will be EO fair because it will have equal false negative rates across two groups. But it has poor accuracy. It has accuracy of only half. Whereas the maximum accuracy classifier, which uses this threshold at half on eta x, that you can show that it is the best possible accuracy. It achieves the best possible accuracy. So the random classifier is fair, but it has poor accuracy. The maximum accuracy classifier is good for accuracy, but is not good for fairness. So there is a trade-off between group fairness and accuracy. Most of the times, like you also see this on the real-world data sets. Here it is just shown on a synthetic data, that there are these two groups, blue groups, and there is a blue group and a red group, and there are these points which are either circles or pluses, and if you these represent the class labels, circles and pluses, and red and blue is the group identity. If you want the accuracy maximizing classifier, here if you think of a linear classifier, the accuracy maximizing classifier is given by this vertical line, and it is accuracy maximizing, but it's not group fair. Like it has different error rates for two groups. For the blue group, it has very low error rate. It can very nicely differentiate the pluses from the circles, whereas for the red group, it cannot really differentiate the pluses from the circles in the red group with that much high accuracy. So there is error disparity here. And whereas if you look at for the same data, if you want to look at the classifier that is group fair, then that optimizes, say, accuracy under group fairness constraint. So among all the classifiers that are fair, if you want to look for the one that maximizes the accuracy, it will be the horizontal line. Now, unfortunately, on this data, it has low accuracy of around 0.5. But depending on the data, you would actually want to do the best possible thing. Like given your data set, you want to maximize accuracy subject to these fairness constraints, and you want to get the optimal fair binary classifier. So the theoretical question here is to characterize the optimal DP or EO fair classifier. That is the classifier that maximizes the accuracy subject to a group fairness constraint, like say equal acceptance rate, that is for DP, that is demographic parity, or equal FNRs in the context of EO fair classifier. Are there any questions? Sorry, I can't see everyone when I'm showing the slide. So if you have any questions, just please feel free to interrupt. Okay, so again, so for characterizing the fair binary classifier, there can be two cases. One is the group aware case, where the feature vector X contains the group membership information Z. And the second is group blind, where the feature vector X does not contain the group information Z. Uh, these are important because both of these are encoded by the formulation that we gave, because the formulation was like you have a joint distribution on x, y, and z. And the thing is, you can always assume that if you are allowed to use z, so at the time of inference, this f, the classifier, if it can use the group information for its prediction, you can assume that there is a copy of z sitting inside x. Otherwise, you assume that the z is separate from x. And so the joint distribution formulation captures both of these, but in practice it is important, like whether you are looking at group aware fair classifiers or group blind fair classifiers, because in certain scenarios you may be prohibited, like legally prohibited from using the group information to make the prediction. So if you look at that example where there are these two curves that are given for two groups, there is a red group and a blue group. And we know that the Bayes optimal classifier, that is the classifier that maximizes accuracy, just puts a threshold of half for everyone. Then you can imagine that suppose you want to make a group aware DP fair classifier. That is, you are allowed to use the group information and do something so that you want to maximize accuracy, but have equal acceptance rates for both of these groups. Then that would mean that currently, if you look at the right of the threshold, the area under the curve for these two groups is not the same, which is what is leading to not having equal acceptance rates for both of them, or that's what is making it DP unfair. So it maximizes the accuracy, but it is unfair for DP. So what would one do to make it DP fair? So the blue population is larger. The area under the blue curve to the right of the threshold is larger than the area under the red curve to the right of the threshold. So ideally, what you would want to do is move the threshold a little bit to the right for the blue population and move the threshold a little bit to the left for the red population, so that the area under the curve for both of these groups on the right of their respective thresholds are equal. And actually, it turns out that the group aware DP fair classifier, the optimal such fair classifier, does exactly this. It applies group aware thresholds. That is, you can show that the optimal classifier, so the optimal DP fair classifier that maximizes accuracy subject to demographic parity constraints, has to apply group aware thresholds on these two populations instead of a uniform threshold of half. Now this cost sensitive, there is a thing called as cost sensitive risk that is associated with thresholds in binary classification. So one can currently, so far, when we looked at, say, the probability, when we looked at the accuracy, it was a 0-1 loss, in the sense that if the predicted label was the same as the true class label, then the loss was 0, otherwise it was 1. If there was a mismatch between predicted label and the true label, then we pay a cost of 1, otherwise we pay a cost of 0 in terms of error. And we are minimizing basically that 0-1 loss or the error rate. But you could imagine that there is a scenario where the risk depends on what the predicted label is and the true class label is. So in binary classification, it would be given by a 2x2 matrix whose entries are, say,Cijs. So C00, C01, C10, and C11. That tells you how much cost you pay when you get when the predicted label is I and the true class label is J. And if these are different Cijs, one can still derive that the classifier for this loss is again a threshold classifier whose threshold is a function of these Cijs. It's not a threshold at half. but it's a threshold whose uh, where the threshold is a function of these CIGs. And for simplicity, you can visualize the simpler case where if the predicted label is the same as the true class label, then the cost is zero. Otherwise, the costs are C and 1 minus C. So basically, you have an imbalance between false positives and false negatives. You care about, say, false positives more than your false negatives, or vice versa. And that is captured by this C and 1 minus C. And the extreme cases of this, like when C is 0 and C equals 1, you would notice that that would sort of mean that you are either very lenient or very strict, and you would have to move the threshold either to very close to 0 or close to 1. So cost sensitive risks are also linked to threshold. Like if you define your risk where you weigh your false positive rates or false negative rates differently on your distribution, then the threshold that you have to that you should use to minimize this cost sensitive risk or this kind of a loss function would be a threshold different from a threshold at half. It will move somewhere, and it will be a function of your cost sensitive risk or the CIJs that define it. So now characterizing, so one question that came up in theory was characterizing optimal fair binary classifier. And there is this paper by Menon and Williamson from 2018, which studies the cost of fair binary classification. What it does is basically it tries to ask this question: can we characterize the optimal DP fair and EO fair binary classifiers? And the idea that they use is this, that they say that pretend for a moment that Z is the label that this classifier F is trying to predict. So far, we thought of Y as the label, and Z was this extra group information. And F of X, we cared about whether F of X equals Y or not. Okay. But pretend for a moment that Z is the label. Think of the distribution. Think of your distribution as X comma Z. You are given a joint distribution on X, Y, and Z. But pretend that your distribution is just the X and Z part of it. And suppose that you are looking at your cost in terms of whether F gets the group membership right. Then, if you look at the two sides of the demographic parity constraints, then the one side becomes false positive rate, like probability that the so this is the acceptance rate from the zero population, that becomes false positive rate, and the acceptance rate from the one population, that becomes the true positive rate. So if you pretend that your distribution is different, you can think of DP also as in terms of false positive rates and true positive rate. And all of these constraints, many of these fairness constraints, like say DP and EO, they can be thought of as minimizing some kind of cost sensitive risk or a different kind of loss. And using this, what Menon and Williamson did is that they said that if you want to maximize accuracy subject to fairness constraint, you can rewrite that problem as minimizing a loss for F. So some loss function, say loss 1 of F with respect to distribution D1 minus lambda times loss 2 of function that classifier F with distribution D2. So you can actually think of it as a linear combination of two such cost sensitive risks on two different distributions. But both of these distributions are derived from the given X comma Y comma Z, the joint distribution on features, labels, and the groups. And a trade-off parameter lambda, which comes from, basically they did this as like, they need this lambda to be given explicitly, but you can also imagine that this lambda comes from basically a Lagrange multiplier. So what they did was they did this, and If you do this, you can actually prove results which characterize the optimal fair binary classifier, which is what they did. And they showed that the optimal group blind fair classifier can be written as an instance dependent threshold. So now the threshold is no longer half for every point, but for every point, it's a different threshold. And if you know the entire distribution x comma y comma z, you would know what are these thresholds to be applied for every point separately. So this is like a mathematical characterization of what the optimal DP fair or EO fair binary classifier would look like. And in the special case, when the classifier is allowed to use the group information, that is, you want the optimal group aware fair classifier, then the threshold is no longer instance dependent. It is just group dependent. Like, it doesn't have to depend on all the features. It can only depend on the group. And it can still achieve maximum accuracy subject to fairness constraints. So this is what they did. The key part was to think of fairness also as a cost sensitive risk. The other thing, like a theoretical tool that one can use, is doing, say, LP relaxation and rounding, those kinds of things that we have seen in theoretical computer science. One can also think of fair binary classification as a linear program. This was implicit in Menon-Williamson, and it was further used by Sellis et al. So what they do is they write this maximization of accuracy subject to, so here I have taken demographic parity constraint, but you can take any other constraint. They actually showed, they call their algorithm as meta-fair because it works for many different kinds of fairness constraints. And also, if you have multiple different constraints, fairness constraints all together, like you may have a DP as well as EO constraint in your optimization. But for now, let's just think of the DP constraint. What one can do is one can write this probability of f of x equals y, which captures the accuracy, as an expectation of this quantity. This is because f is 0, 1. It's a 0, 1 valued. It's a binary classifier. So this probability that f equals y can be written as this expectation. Only when f and y are the prediction and the true label, they are the same, this will get counted. Otherwise, it will not get counted. Okay, so this is maximizing accuracy subject to the DP constraint. The DP constraint can also be written as expectation of f of x conditioned on the group being 0 minus expectation of f of x conditioned on the group being 1 equal to 0. Now notice that if you think of this whole thing as a program with variables f of x. So f of x is what you want to find out. What is the optimal fair classifier will be given by, if you knew the value f of x for every feature vector x, then the classifier would be completely characterized. There could be infinitely many such, like your feature space may be infinite. But for now, think of this as like an infinite LP with these 0, 1 integer variables f of x. If you had all of these variables, this function will be a linear objective in these variables. And you can also notice that the DP constraint is also a linear constraint in these integer variables. And one can also do similar things even when the constraints are equal opportunity or many other kinds of fairness constraints that are standardly studied. Sometimes they may not be linear constraints, but there are some other ways, like these could be like fractional constraints that people also look at. But for now, this is like a very simple, nice formulation which says that when you are trying to maximize accuracy subject to demographic parity constraint, essentially what you are doing is you are solving a huge linear program, integer linear program. Now, what would you do if you have such a thing? You would basically relax the program to have variables not integer valued, but variables that take values between 0 to 1 in the interval 0 1. You relax and you solve. Now, suppose there were no fairness constraints, then how would this look like? You would only have this objective subject to these variables being between 0 to 1. The f of x variables will be real valued between 0 to 1. And you would write this expectation as, so it's a joint expectation over x comma y comma z. Here at least z does not matter, x and y matter. But this expectation, you can write it as expectation over x, f of x times this. So you can collect the terms together. So expectation of f of x times 2y minus 1 plus expectation of 1 minus y. And then that expectation of 1 minus y is just probability that y equals 0. And the first part is just expectation over x of f of x times 2 times eta x minus 1. Okay, where eta x is, so we have pushed the probability on y conditioned on x inside and replaced that 2y minus 1 with 2 eta x minus 1, where eta x is probability of y equals 1 conditioned on x equals little x. And this actually is what it looks like without any fairness constraints. And this is what leads to the Bayes optimal classifier, because now if you stare at this objective, it will tell you that if your f of x is taking values between 0 to 1, and if you want to maximize this, basically whenever eta x is less than half, you should make f of x as 0, and whenever eta x is greater than or equal to half, you should put f of x as 1. You should put all the weight there. So this leads to the Bayes optimal classifier. The only difference in fair binary classification is that there is this constraint, and you can use Lagrange multipliers to move that constraint to the objective, where there will be this plus lambda times the constraint based thing that will come up. And one can derive an expression for the optimal fair classifier also similarly, where you would have a term not just based on eta x, but you would have terms which would be based on eta ij of x, where each eta ij of x will be probability of y equals I and z equals j conditioned on x equals little x. And one can derive a similar expression for the optimal fair classifier using Lagrange multipliers. And as we saw, interestingly, this happened also in the context of Bayes optimal classifier, that the optimal solution is actually integral. So you can relax, but you can actually, eventually you will see that this looks like an LP. You can relax it and solve it, but its optimal solution is an integral solution. And it helps you characterize the fair binary classifier in terms of these eta ij of x. Just like Bayes optimal classifier used eta x, the optimal fair classifier can be characterized using a function of eta ijx, where eta ij of x is probability that y equals I and z equals j conditioned on the features being little x. So let me tell you now a little bit about group fair representations. So people have also looked at these fair classification. So we saw that there is a trade-off between accuracy and fairness. And if you want the optimal fair classifier, then you need to solve this constrained optimization. People look at representations, where representation is a mapping from the original feature space to another representation or embedding space, where say the features x they map to, or the random variable corresponding to the feature. So this x maps to r of x, and such embeddings like say word to vec or bird, they are commonly used, or some pre-processing that people do, you can also think of that as representation, like changing the data distribution. They are common in practice. And group fair representation means that any classifier on the induced distribution must be group fair. So the representation itself gives this guarantee that all classifiers on that induced representation are group fair. For example, DP fair or EO fair. So fairness is guaranteed. All that you have to do is maximize accuracy. So on the original data, you would uh, basically maximize accuracy subject to fairness constraint, where if you have this guarantee of fairness through this representation, all that you have to do is maximize just the for the accuracy. Now the thing is, uh, here you may have to pay some price of fair representation, right? Because if uh, if you look for maximizing accuracy subject to DP fairness on the original distribution, you might be able to achieve some accuracy. Now the representation has this restriction that on the representation every classifier has to be group fair, and among such classifiers you are maximizing accuracy, so you are kind of restricted in a way. So the maximum accuracy you can achieve, you might think that it is less than the optimal fair accuracy, like optimal accuracy of a fair classifier you could have achieved on the original distribution. So this is what, let's call this as price of fair representation. Uh, Turns out that like you would pay some price of fair representation, and you can look at these representation in like deterministic representations as well as randomized representations. A theoretical question that one can ask is how much do you pay as price of representation when you look at these group fair representations. And it turns out that one can actually construct distributions over which any deterministic representation must pay a non-zero or non-trivial price of group fair representation. Whereas on the other hand, if you look at randomized group fair representations, if you are allowed, if this R of X is allowed to be randomized in the sense that for every feature vector, it can map it to R of X using, say, randomness. So it can toss a fair coin and the same feature point may get mapped to one versus the other based on some probability. That means you can
Hello.
redistribute. Yes.
Sir, one doubt on the price of fairness in the previous slide.
Uh-huh.
So the fair representation price, if we have the fairness constraint, should be less than the optimal accuracy, right? Without the fairness constraints.
Correct. Correct.
So
So
isn't the definition other way around? The minus, I mean, the price of fair representation.
okay. So the thing is, the representation. If representation is identity representation, then you are right that the maximum accuracy you can achieve on XYZ joint distribution is higher than the optimal accuracy on uh, of a fair classifier on XYZ. But the identity representation is not a group fair representation because it doesn't satisfy this property that every classifier on XYZ is fair.
Okay, because of the Z constraint, because of the
Yes.
group, it's different.
So
Okay.
yes. So if R is group fair, then that means R is special in some way. That every classifier on this R of X comma Y comma Z is fair because it's only operating on R of X.
Okay, so and so how does this deal with imbalance data? I'm a bit fan. Does fairness work well with imbalance?
Yes. So what do you mean by that? I mean, all of
Uh,
these definitions hold for any data distribution, say DP
okay,
fairness or EO fairness, and they are again looking at say acceptance rate or false negative rates conditioned on that distribution, on the group wise distribution. So if the groups are imbalanced, still you can insist on equal FNRs, right?
got it. Thank you, sir.
Although if you just try to maximize an aggregate metric, so one of the reasons why these are conditional probabilities is because if you try to maximize something that is aggregate, like just if you try to maximize accuracy on the overall data and the groups are imbalanced, then you would not get equal accuracies on the two groups. It may happen that one group is underrepresented. So if when you look at overall accuracy, you don't care so much for that underrepresented group. So if you just want to maximize overall accuracy, you might have different accuracies on different groups. So when uh, one thing that I can say is that if you try to look for aggregate metrics, then this data imbalance is an issue. And that's why all of these fairness metrics are basically equal accuracy conditioned on the group or equal FNRs conditioned on the group. So I won't tell you this proof of this these two results, like why say if you go from deterministic to randomized group fair representation, uh, the randomized group fair representation pays zero price of fair representation. But it's kind of related to these other results that we saw earlier, Menon Williamson and Celis et al. That if you are allowed randomized group fair representation, you can make sure that you don't lose anything in the accuracy compared to the accuracy of the fair classifier on the original data. So this is a joint result with Sushant Agarwal, which appeared in Fact. So for all of these questions, like even here, the thing is, one question is, can we construct group fair representations efficiently? Uh, in practice, you may not want exact DP fairness, but even with say approximate DP fairness. And this has a clear practical motivation that sometimes say there is a regulator or say government that wants to release some data, and they want to make sure that whoever uses this data and builds whatever model they want to build, they must satisfy a certain property. Like it should not happen that like it should not happen that somebody downstream develops a model that does not satisfy fairness. So I want to, as a regulator or a government, if I'm releasing the data, I want to make sure that I release it not as the original data, but as some representation, such that whatever models that are built on top of that, they must satisfy a certain property, like say at least some fairness. You could also think of these for robustness, privacy. So these representation based questions are another space of interesting questions for theoretical exploration. But now let's take a step back to think about thresholds. So we realize that there are these results that characterize optimal group fair classifiers, and they show that the optimal group fair classifiers, they are actually instance dependent threshold classifiers on the true risk. One question is basically, can we compute these group fair classifiers efficiently from training data with provable generalization guarantees? Like we want some sample complexity bounds and generalization guarantees. This is like an open question at this point. There is some partial progress that has been made in previous work, but by and large, like this is a theoretically open question, which is very interesting. But another question is like, are group dependent or instance dependent thresholds truly fair? I mean, they are fair in terms of these outcomes. Yes, they achieve maybe equal acceptance rates or equal FNRs. But because they apply different thresholds to different individuals, so two individuals, so there may be 2 points, x1 and x2, that have the same true risk or similar true risk. Let's say eta of x1 is very close to eta of x2. But the threshold t of x1 may be different from the threshold t of x2, which is why when we apply these thresholds, the optimal fair classifier, uh, it gives very different predictions for these two individuals. So in that case, it may happen that instance dependent thresholds may not be fair to individuals, or they may not be. This can be thought of as individual fairness as well as a robustness issue, because we are saying that two individuals that are similar in the feature space, and not just in the feature space, also in terms of their true risk, are treated differently. So, what do different thresholds mean in terms of cost sensitive risk? So, as we saw, that thresholds are related to cost sensitive risks. And it basically means that if you are using different thresholds for two different points, then it essentially means that we weigh their false positives and false negative outcomes differently for these points. So, in other words, basically these optimal fair classifiers, what they are doing is they are treating or weighing the false positives and false negatives differently for different points. And one may argue that this is group fair, but it's not fair to individuals. So one of the things that we did was this led us to think of something called as inframarginality. So inframarginality quantifies how much a classifier deviates from being a threshold classifier on the true risk probability of individuals. So the base classifier that maximizes accuracy, it applies the same threshold of half to all the individuals. It means, so basically, I haven't defined inframarginality formally, but this says that it has zero inframarginality. Whereas if you look at a random classifier has high inframarginality with respect to any threshold. Because even if, say, two individuals have the same eta x or the same probability of y equals 1 conditioned on x equals little x, when we toss a random coin, one point may get outcome 1, whereas the other point may get outcome 0. So a random classifier has high inframarginality with respect to any threshold. It deviates far from any threshold classifier. So what we did was we formalized this notion in terms of how much. So if you take a threshold classifier, it has some outcomes. And if you take some other classifier, then how often do these outcomes for these two classifiers agree? It tells you basically, and that can be used as the formal definition of inframarginality. And you can use this to audit some group fair classifiers to see how inframarginal they are. So how much, so basically high inframarginality would mean that they treat similar individuals very differently, and they are very far from a threshold classifier against which we are comparing them. So this was joint work with Arpita Biswas, Siddharth Burman, and Amit Sharma in FORC. So what we did was we did this inframarginality audit of group fair classifier. And it turned out that if you look at some of the group fair classifiers, they can be individually very unfair. So there was this lambda parameter that I told you. In a way, if you look at the meta-fair classifier of Sellis et al., it characterizes the optimal group fair classifier, but they have this characterization in terms of lambda, where higher the lambda means you are satisfying the group fairness constraints more strictly. Lambda equals 1 would mean like perfect group fairness. So they did this for like this plot shows it for false discovery rate based fairness. Like just like we can define equal acceptance rates or equal false negative rates, false discovery rate, equality of false discovery rates across groups is also used as a group fairness metric. And if you look at the meta-fair classifier that tries to equalize the false discovery rates, as lambda increases, its inframarginality also increases. And there is an epsilon here which we use to basically say we are okay with individuals being treated differently in a small epsilon interval around the threshold. But we are not okay with treating individuals differently beyond that threshold. Like somebody who is, so for example, if you are close to being to the base optimal classifier that uses a uniform threshold of half for everyone, it's okay to get confused between individuals who have true risk may be 0.51 and 0.49. But it's not okay to get confused between individuals whose true risk is like 0.99 and zero point 0.1. So this epsilon tells you how, if you discount this epsilon interval, so when you are discounting an interval, epsilon interval of zero point 0.5 on either side, basically it means we are looking at individuals who are very high risk and very low risk. And a group fair classifier, just to satisfy group wise statistics, it may be highly individually unfair. So if you look at fairness in this different way, it also tells you about like these individual fairness metrics. One can also use them as constraints. And some of the results which were about characterizing fair classifiers subject to these group fairness constraints, one can also extend these to doing characterizing fair classifiers subject to group fairness as well as these inframarginality based constraints. Now the thing is, like inframarginality audit, one can have a criticism of all of these results, saying that all of these results, they need the true risk probabilities eta of x, and also the characterization requires eta of x or eta ig of x, and otherwise we cannot do characterization, and inframarginality audit can also not be done. But one can actually show that many of these can be done even with good estimates of the true risk probabilities under reasonable assumptions. So I won't get into like the technical details of these, but these can be done with even assumptions which are reasonable assumptions on eta of x, or for practical applications, if you can somehow get good estimates of them and do these, you can still prove some results about the fairness accuracy guarantees. In case of inframarginality audit, you can say that the inframarginality audit is not very the inframarginality that you observe is not very far from what you would have observed if you had the exact values. Now to give you maybe change tracks, and I can give you a couple of other examples. Like fairness in ranking is also a question where people have looked at representation based fairness. And to give parallels to this under ranking, the questions there are whether group fair, so group fair ranking means the simplest example would be each item has some utility, each position has some utility, and one can look at basically ranking the items so as to maximize the overall utility. And you would put, basically it happens that these positions, they have their utilities are decreasing. The items, you want to put them in the decreasing order of their utilities and fill those positions, so that greedy algorithm would maximize the total ranking utility. People have also looked at other kinds of ranking utilities, but this is the simplest one. And representation based fairness means that you want, apart from doing this, you want, so instead of just ordering them by their utilities, the item wise utilities, you want to satisfy some fairness constraints. Like you would want equal representations for groups in the top k ranks or the top prefixes. And individual fairness in learning to rank has also been considered, where the importance of positions, you can think of it as the probability of, in ranking or recommendation, that's the probability of clicking on that result. And that clicking gives exposure to items, and you want similar exposure for items with similar features, or you want similar exposures for items coming from two different groups. And people have studied this question of group fair ranking. Can we do maximization of ranking utility subject to representation based constraints on top k or all prefixes or some of the prefixes? You can also have these representation based constraints for some of the prefixes, if not all. And there are results which show that you can again use algorithms similar to greedy algorithm. And more interestingly, you can also use these ideas about writing LP relaxations and showing that they are integral. So group fair ranking has been studied. The other set of questions are basically like to draw parallels with this group fairness and individual fairness. Is group fair ranking anti-meritocratic? So these, I'm calling this as re-ranking because here at least we are not touching the part which is doing learning to rank. In machine learning, you have lots of labeled data and you do like you learn a ranker from them. Here, think of it as you have already learned a ranker, which maximizes ranking utility, and that has been trained on the training data. And you just want to do a re-ranking to satisfy certain fairness constraints. And here one can think of this question, which is group fair re-ranking anti-meritocratic? That it maximizes the aggregate ranking utility, but does it re-rank individuals too low compared to their true rank? And similar to this inframarginality that came up in the group fair classification, we studied this question of worst case displacement, multiplicative displacement of an individual's rank uh, after the group fair re-ranking. And there are trade-offs between group fairness and under ranking. And one can actually look at the problem of satisfying group fairness while so maximizing ranking utility subject to group fairness as well as under ranking constraints, or minimizing just say the under ranking subject to group fairness constraints. And these kinds of questions also one can look at. This is joint work with Shruti Gorantla and Anand Lewis that appeared in ICML. I'm just giving you an overview of the kind of theoretical and algorithmic questions that come up. Like we had an algorithm that generalized a previous greedy algorithm used for group fair ranking, so that it also incorporates the under ranking constraints. And one can get the best of both worlds. Like one can show that you can get simultaneously a group fairness guarantee that is comparable to the best group fairness algorithm, as well as under ranking that is comparable to basically the utility maximizing ranker. uh, I will not get into, I mean, I don't have enough time, but I can maybe just tell you a little bit about, just like fairness, one can also think of robustness, where we saw that for individual fairness, it meant treating similar or close individuals that are close in feature space to be treated similarly. Robust, it is actually very close to robustness, because robustness requires that two uh, points that are close in feature space should not get very different predictions. But for many of these models, especially on image data, it has been observed that you can do these adversarial perturbations that are very small pixel-wise perturbations that are imperceptible to humans, but they change the prediction by a lot. I mean, they make the model misclassify and highly like misclassify. It can have a model that has very high accuracy can suddenly have very low accuracy if you change all the test images just by a tiny pixel-wise perturbation. Sometimes even by the same perturbation that is applied to all of them. Uh, the other thing that one can study is like even in robustness, one can study different kinds of robustness. So this is like adversarial robustness is robustness to malicious perturbations. But there are also natural perturbations, which are geometric transformations of images, like say translations, rotations, scaling, and so on. And people have studied these theoretically and developed models. Like in case of neural networks, convolutional neural networks are supposed to be like they are supposed to promote translation based invariance or translation invariance in the predictions. Similarly, one can do this for different kinds of transformation groups, and there have been invariant models that have been developed. And uh, one of the things that we studied was like trade-off between spatial and adversarial robustness. And the mitigation strategies, or to make models robust for to adversarial perturbations, people do something called as adversarial training. Whereas to make models robust to spatial perturbations, people do data augmentation, like add lots of these translation rotations, etc., scaling in the training data, and also use models that are architecturally designed to have this invariance. And we observed that there was a trade-off between these two. Like if you try to use the existing methods make to get one kind of robustness, you perform poorly for the other, and vice versa. And we proposed a method that could balance these both. But okay, I think I will stop here just by giving these after giving these examples. To give a quick summary, there are like classification, ranking, recommendations are some of the important applications that come up, and that have like societal and economic impact. And there are good theoretical and algorithmic questions there that can be studied. Some of these are very simple algorithmic questions or theoretical questions that are related to mathematical characterizations of, say, the optimal classifier or the optimal ranker that satisfies some properties. You could also ask this about like optimal regression subject to fairness constraints. You could also ask this for robustness. So there are good theoretical questions that can be studied which are related to mathematical characterization. But there are also algorithmic questions about how you can you efficiently construct any of these objects, and can you use them. Also, one thing that I kind of did not touch upon was, many times what happens in practice is that you can think of these as pre-processing, in-processing, and post-processing questions, where representations like learning good fair representations or private representations could be thought of as like pre-processing. There is a data, you want to pre-process it such that most models or any model that you learn on top of that would have this property. One can also ask this in, say, fair ranking, that people do pre-processing where they pre-process the training data, so that if you learn a ranker on top of that, it would have some fairness guarantees. Even in classification, like the representation result I told you was about pre-processing. In processing means that there is, like, say, a learning to rank method, and you want to, inside that, the optimization that happens, you want to change that so that its outcome would be fairer. Or even in classification, you want to learn from a certain parameter space, you are, or learning from a hypothesis class, you want to make sure that your learning algorithm is fair, that is, it is guaranteed to give some fair classifier as its outcome. And the third is post processing, like this re-ranking algorithm that I mentioned in the context of group fair ranking, where there is a model that is learned. All that you have to do is, it has some utility, it's some utility maximizing model, and you know what utility function it is using. All that you want to do is, you want to post process the output of the model so as to not decrease its utility by much, while satisfying certain fairness guarantees or robustness guarantees. So all of these questions can be divided into like pre-processing, in-processing, and post-processing. And all of these are quite valuable. And you could also think of the post-processing as also maybe in and post, some combination where you are allowed to change the model. So many times people deploy a model, find that it has certain problems, and you, as a way of fixing the model, you don't want to train the model from scratch again, or you don't have access to its training data, so you cannot do pre-processing. All that you can do is, you can do some small changes to the outcome of the model or certain parameters of the model, so as to incorporate some properties in it. So with that, I will stop. If you have any questions, you can ask me, or you can email me later, if that is also fine.